Time crystals are synthesized and studied within an advanced quantum laboratory. Sophisticated equipment is essential for the creation and analysis of time crystals. The quantum lab provides a controlled environment for observing the unique properties of time crystals. Time crystals are created using specialized apparatus under precise experimental conditions. The apparatus allows for meticulous control over the quantum environment required for time crystal formation. Precision is essential to successfully synthesize and observe the unique properties of time crystals. Time crystals are a novel phase of matter exhibiting periodic structure in time rather than space. The creation of time crystals involves meticulous parameter adjustments to control quantum interactions. Unlike conventional crystals, time crystals spontaneously break time translation symmetry. Atoms arrange themselves in a repeating, ordered pattern known as a crystal lattice. The crystal lattice structure determines the macroscopic properties of a material. Defects within the crystal lattice can significantly alter a material's behavior. Atoms within a crystal exhibit constant motion, pulsing and oscillating in a repeating pattern. This inherent motion demonstrates the dynamic nature of matter at the atomic level. The repeating pattern of atomic oscillation contributes to the overall stability and properties of the crystal. At the atomic level, particles exhibit continuous motion. This perpetual motion occurs without any external energy input. The motion is inherent and spontaneous at this scale. Temporal symmetry describes systems that behave identically whether time moves forward or backward. In temporal symmetry, reversing the direction of time does not alter the system's fundamental behavior. Visualizing temporal symmetry helps understand fundamental concepts in physics and other sciences. Temporal symmetry breaking is characterized by systems exhibiting periodic motion that lacks time reversibility. Time crystals break temporal symmetry through self-sustained oscillations without external energy input. The periodic motion of time crystals is not time reversible, indicating a fundamental asymmetry in their temporal behavior. Temporal symmetry breaking indicates a system's state differs at various points in time, even after completing a full cycle. Visual cues highlight the distinction between the crystal's initial and final states after a complete cycle. The crystal's evolving state demonstrates that it does not return to its original configuration, breaking temporal symmetry. At the atomic level, particles exhibit oscillatory motion. Broken temporal symmetry implies that the behavior of these particles is not identical when time is reversed. This asymmetry suggests a fundamental difference in particle behavior over time. A crystal's motion is determined by its internal atomic structure. The internal structure, not external forces, dictates the crystal's movement. Understanding the atomic arrangement within a crystal is key to predicting its behavior. Time crystals exhibit a form of perpetual motion by oscillating in time without energy input. The classification of time crystals as perpetual motion hinges on the definition and interpretation of motion and energy. Unlike classical perpetual motion machines, time crystals do not violate the laws of thermodynamics due to their unique quantum properties. The crystal's continuous movement does not violate thermodynamics because it exists in a non-equilibrium state. Perpetual motion requires a system to operate without energy input or loss, which is impossible under normal conditions. Non-equilibrium states allow for continuous movement by utilizing energy gradients, differentiating them from perpetual motion machines. The crystal's continuous motion is powered by quantum mechanics. The crystal does not extract energy from its surroundings to maintain its motion. Quantum mechanics sustains the crystal's motion indefinitely. Quantum mechanics governs the behavior of time crystals, dictating their unique properties. Time crystals exhibit perpetual motion in their lowest energy state, a phenomenon explained by quantum principles. The quantum mechanical framework explains how time crystals break time translation symmetry. Quantum entanglement describes a phenomenon where two or more particles become linked, sharing the same fate no matter how far apart. Quantum superposition allows a quantum system to exist in multiple states simultaneously until measured. Quantum entanglement and superposition explain the unique properties observed in certain crystalline structures. Time crystals represent a novel phase of matter exhibiting periodic structure in time. These crystals are a manifestation of quantum phenomena observable at a macroscopic scale. Time crystals challenge traditional understanding by spontaneously breaking time translation symmetry. Time crystals hold potential for use in quantum computing due to their stable, predictable behavior at the quantum level. The unique properties of time crystals may enable the creation of highly precise timekeeping devices. Time crystals' inherent stability and self-sustaining oscillations could revolutionize various technological applications. Time crystals' stable, periodic motion can be utilized to create more robust quantum bits, qubits. The inherent stability of time crystals offers enhanced coherence and reduces errors in quantum computations. Using time crystals and qubits allows for more reliable and scalable quantum computing architectures. Time crystals' precise oscillations may enable more accurate atomic clocks. Improved atomic clocks can significantly enhance precision timekeeping applications. The stability of time crystals offers a potential pathway to next-generation timekeeping technology. Scientists are actively researching time crystals within the quantum lab environment. Time crystal research involves intricate experiments and data analysis to understand their unique properties. The lab setting facilitates the study of time crystals through controlled experiments and advanced measurement techniques. Scientists analyze data from quantum experiments to refine their understanding of unique quantum structures. The experiments aim to push the boundaries of knowledge regarding quantum phenomena and their underlying principles. Refinement of experimental setups and data analysis are crucial for advancing quantum research and innovation. Ongoing research continues to explore the fundamental properties and potential applications of time crystals. Many unanswered questions remain regarding the long-term stability and scalability of time crystal technology. Future studies aim to uncover new methods for synthesizing and manipulating time crystals for advanced technological applications. The study of time crystals is a rapidly evolving field. Time crystals hold the potential to revolutionize our understanding of physics. Future research may unlock new properties and applications of time crystals. The study of time crystals opens new avenues for future scientific exploration. Future discoveries in time crystal research may revolutionize fields such as quantum computing and material science. The potential applications of time crystals inspire wonder and anticipation for future technological advancements. Atoms are in constant motion, a fundamental characteristic of matter at the microscopic level. The intensity of atomic motion is directly proportional to temperature. Higher temperatures result in faster atomic movement. Atomic motion is crucial for various physical and chemical processes, including diffusion and chemical reactions. Temporal symmetry refers to invariance under a time reversal transformation. In a temporally symmetric system, the laws of physics remain the same, whether time runs forward or backward. Temporal symmetry implies that past and future are equally governed by physical laws. Perpetual motion describes a system that can operate indefinitely without any external energy source. The laws of thermodynamics preclude the existence of true perpetual motion machines due to energy loss from friction and other factors. Despite theoretical impossibility, the concept of perpetual motion remains a valuable thought experiment in physics and engineering. Quantum mechanics describes the behavior of matter and energy at the atomic and subatomic levels. Wave-particle duality posits that quantum entities exhibit both wave-like and particle-like properties. Quantum entanglement links two or more particles in a way that their fates are intertwined, regardless of the distance separating them. Potential applications are diverse and span multiple sectors. These applications can address various challenges and improve existing processes. Real-world implementation demonstrates the practical benefits of these applications. The quantum lab is a controlled environment designed for conducting experiments at the atomic and subatomic levels. Quantum experiments require precise control over environmental factors, such as temperature, vibration, and electromagnetic interference. Sophisticated measurement and control systems are essential for manipulating and observing quantum phenomena. Future research aims to expand current knowledge and explore new possibilities. This research seeks to address existing limitations and improve upon current methodologies. The outlook for future research is optimistic, promising significant advancements and innovations. Atoms are arranged in a lattice structure. The lattice structure defines the material's properties. Defects in the lattice structure can affect the material's behavior. Crystal lattices are characterized by a highly ordered, repeating arrangement of atoms. Imperfections disrupt the perfect order of the lattice, influencing material properties. Point defects, such as vacancies, are a type of imperfection in the crystal lattice. Crystal imperfections disrupt the perfect periodic arrangement of atoms. Point defects, such as vacancies and interstitials, alter the local electronic structure and mechanical properties. Line defects, or dislocations, significantly reduce the yield strength and increase the ductility of crystalline materials. Quantum entanglement links two or more particles, creating a shared fate regardless of the distance separating them. Measuring the state of one entangled particle instantaneously determines the state of the other, even across vast distances. Entanglement is a fundamental quantum phenomenon, with potential applications in quantum computing and quantum communication. Quantum superposition describes a quantum system existing in multiple states simultaneously. Measurement forces the system to collapse into one definite state. Before measurement, the probabilities of each state are described by a wave function. Quantum computing utilizes qubits to represent information, leveraging quantum mechanical phenomena. Time crystals can be used as a physical representation of qubits in quantum computing. Qubit representation via time crystals offers potential advantages in quantum information processing and storage. Atomic clocks provide extremely precise timekeeping based on the consistent resonance frequency of atoms. The accuracy of atomic clocks is utilized in various applications requiring high precision timing. Atomic clocks are essential for synchronizing global communication networks and financial transactions. Control systems are visualized to monitor and manage quantum experiments. Visualization interfaces display real-time data from quantum processors and related environmental controls. Visual representations aid in optimizing quantum system parameters for enhanced stability and accuracy. The long-term stability of time crystals under varying environmental conditions remains an open question. Further research is needed to understand how external perturbations affect the quantum coherence of time crystals. Investigating the effects of impurities and defects on time crystal behavior is crucial for practical applications. Atomic spin is a fundamental property of elementary particles, including electrons, protons, and neutrons. Spin is a quantized property, meaning it can only take on specific, discrete values. Atomic spin contributes to the magnetic properties of materials. Atomic spin influences the motion of atoms within a crystal lattice. The collective spin of atoms can generate forces that drive crystal deformation. Changes in atomic spin alignment can induce macroscopic motion in crystalline materials. Temporal symmetry implies that the laws of physics remain consistent regardless of the direction of time. In systems exhibiting temporal symmetry, reversing the direction of time does not alter the system's fundamental behavior. Classical physics largely assumes temporal symmetry, although this may not hold true at quantum levels or under extreme conditions. Perpetual motion is impossible due to the fundamental laws of thermodynamics. The second law of thermodynamics dictates that entropy, or disorder, always increases in a closed system. Energy dissipation through friction and other forces prevents any real-world system from achieving perpetual motion. Quantum tunneling is a phenomenon where a particle can pass through a potential energy barrier that it classically cannot surmount. The probability of tunneling depends on the particle's energy, the barrier's width, and the barrier's height. Quantum tunneling plays a crucial role in various physical processes, including nuclear fusion in stars and semiconductor devices. Quantum error correction utilizes time crystals to enhance the stability of quantum information. Time crystals provide a robust framework for detecting and correcting errors in quantum computations. The unique properties of time crystals enable more reliable and fault-tolerant quantum computing architectures. Time crystals enable highly precise timekeeping applications. The unique atomic structure of time crystals allows for unparalleled accuracy in clock mechanisms. Time crystal clocks offer enhanced stability and reduced drift compared to conventional timekeeping devices. Quantum data analysis involves complex algorithms to interpret probabilistic outcomes. Superposition and entanglement are key quantum phenomena utilized in data processing. Quantum error correction is essential for maintaining data integrity during computations. Creating large-scale time crystals presents significant challenges in maintaining their delicate quantum coherence. Scaling up time crystals requires precise control over environmental factors to prevent decoherence and maintain stable oscillations. Current research focuses on overcoming material limitations and developing robust methods for synthesizing and characterizing large time crystals. Phonons are quantized modes of vibration occurring in a rigid crystal lattice. These vibrations propagate as waves, transporting energy and momentum through the material. Phonons play a critical role in determining a material's thermal and acoustic properties. Phonon are quantized modes of vibration occurring in a rigid crystal lattice. Phonon interactions influence thermal conductivity by scattering heat carrying phonons. Crystal properties like thermal expansion and specific heat are affected by phonon behavior. Symmetry breaking is observed in various physical systems beyond fundamental physics. Examples include the formation of crystals, where the initial symmetry of the liquid state is broken as the crystal lattice forms. Fluid dynamics also exhibit symmetry, breaking through phenomena such as the Barnard convection cells. Time crystals exhibit a unique form of perpetual motion at the quantum level. Energy conservation principles apply to time crystals, despite their continuous motion. The motion in time crystals does not violate thermodynamic laws due to its quantum nature. Quantum decoherence is the loss of quantum coherence, where a system's superposition states collapse into classical states due to interaction with the environment. Environmental interactions, such as measurement or thermal fluctuations, cause quantum systems to decohere. Decoherence explains why quantum phenomena are not typically observed in macroscopic systems. Quantum computing utilizes time crystals for quantum memory applications. Time crystals offer a stable and coherent medium for storing quantum information. Quantum memory, based on time crystals, enhances data processing and computational efficiency. Time crystals offer potential applications in precision timekeeping. The stability of time crystal clocks is a key advantage for accurate time measurement. Time crystals maintain consistent oscillations, enhancing the reliability of timekeeping applications. Experiment design involves carefully planning and structuring the procedures to test a hypothesis. Key elements include defining variables, controlling conditions, and establishing measurement protocols. Effective experiment design ensures reliable data collection and valid conclusions. Time crystals exhibit unique structural order that repeats in time rather than space. The novel properties of time crystals may enable the creation of new materials with advanced capabilities. Future research aims to explore the potential applications of time crystal principles in material science. Magnons are collective excitations of electron spins in a magnetic material. These excitations can be visualized as quasi-particles that carry spin wave, momentum, and energy. Magnons play a crucial role in understanding the magnetic properties of materials at the nanoscale. Magnons, as collective excitations of electron spins, influence the magnetic properties of crystalline materials. The presence and behavior of magnons affect a crystal's overall magnetic order and susceptibility. Magno-phono interactions modulate thermal conductivity and other physical properties within the crystal. Time reversal symmetry implies that the laws of physics are unchanged under the transformation T. If a process is allowed by the laws of physics, so is the time-reversed process. Not all physical phenomena exhibit time reversal symmetry at the fundamental level. Zero-point energy refers to the lowest possible energy state a quantum mechanical system may have. Even at absolute zero temperature, quantum systems retain vibrational energy due to the uncertainty principle. Zero-point energy is a theoretical foundation for potential perpetual motion, though harnessing it remains a significant scientific challenge. Quantum field theory describes elementary particles as excitations of underlying quantum fields. These quantum fields permeate all of space and time, governing the behavior of matter and energy at the smallest scales. Quantum field theory reconciles quantum mechanics with special relativity, providing a comprehensive framework for particle physics. Quantum sensors utilize time crystals for enhanced measurement precision. Time crystals provide stable, self-repeating states that improve sensor accuracy and sensitivity. Quantum sensors with time crystals offer potential applications in various fields, including metrology and fundamental physics research. Time crystals can be used for precision timekeeping applications. Time crystal clocks offer potential improvements in accuracy and stability compared to traditional atomic clocks. Time crystal calibration can improve the synchronization of global timekeeping systems. Quantum simulations utilize computational models to replicate and analyze quantum systems. These simulations enable researchers to explore quantum phenomena and predict system behaviors. Simulation software provides a virtual environment for quantum experimentation and analysis. Time-based technologies present unique ethical challenges regarding privacy, autonomy, and societal impact. Algorithmic bias in time-sensitive predictions can perpetuate discrimination and inequity. The use of time-based technologies requires careful consideration of transparency, accountability, and fairness. Domain walls are interfaces separating regions of uniform order parameter. These walls represent areas where the order parameter changes gradually. Domain walls can be visualized as a transition zone between different ordered states. Domain walls are interfaces separating regions of uniform magnetization in a crystalline material. The motion of domain walls is crucial for understanding the magnetic properties and behavior of crystals. External magnetic fields or applied stress can induce the movement of domain walls, affecting the crystal's overall magnetic state. Spontaneous symmetry breaking is a process where a system's state lacks the symmetry of its underlying laws. This breaking occurs when the system settles into a state that does not reflect the full symmetry. Spontaneous symmetry breaking is a key concept in various fields, including particle physics and condensed matter physics. Perpetual motion is impossible, according to the laws of thermodynamics. Non-equilibrium thermodynamics studies systems that are not in thermodynamic equilibrium. Real-world systems are often in non-equilibrium states, requiring continuous energy input to maintain their organization. Quantum gravity seeks to reconcile quantum mechanics with general relativity, addressing gravity at the quantum scale. One implication of quantum gravity is the potential quantization of spacetime itself, suggesting a discrete, granular structure. Quantum gravity may lead to modifications of the uncertainty principle and Lorentz invariance, impacting our understanding of fundamental physics. Quantum simulators use time crystals to model complex quantum systems. Time crystals, as non-equilibrium matter, provide a stable platform for simulating quantum phenomena. These simulations enable the study of quantum materials and the development of novel quantum algorithms. Time crystal clocks offer enhanced precision in timekeeping applications. The stability and accuracy of time crystal clocks are crucial for advanced navigation systems. Time crystal technology improves the reliability and accuracy of global positioning systems.